Does anybody have any questions about what we were talking about previously? I'm gonna talk about this again a little bit. So at the very end of class last time, we talked about flatness and tensor products. And the one thing that I mentioned is that since it's an adjoint functor, then it's going to be so it's a left adjoint, right? So it's going to be right exact. So it's going to preserve surjections, and I'll talk about that in a second. Okay, so this is about tensor products and flatness. Okay, so this is, I guess, part 2. But we barely got into it. So I just kind of said that someone says, what's flat mean? Then I said there exists this functor. It's the left adjoint of the functor represented by a module. So that's tensor product with the module. And just from like abstract category, just from category theory, if you have this left, if you have a left adjoint, so left adjoints preserve co-limits, right adjoints preserve limits, and co-limits are like co-kernels, and it means that so surjections will be preserved by this thing, so that you get this tensor functor and it'll be right exact. Okay, and so so there's an explicit description of tensor products. So decline. Pretty sure that's about a like a what is that scam that they're doing? Like your extended warranty on your car.
That's the one I get most often.
Yeah, pretty sure that was one of those.
Though I did get one recently that it was something to do with my social security number, and I thought, no.
No. Okay. Okay, so let me give you the explicit description of the tensor product of two modules. Tensor product. Let me just do explicit description so you guys will see what I mean. So given two R modules, V and W. So we have this thing. So this is a little cross with a circle around it. So it shouldn't look like a, so there's two symbols. There's the direct summand, which is a circle with a plus in it, and this is a circle with the times in it. So this is the tensor product of V and W over R. Okay, and so it is the free module. It is the free R module spanned by the symbols okay, so we're gonna have a bunch of symbols. So V tensor R W. Okay, sometimes I'm gonna omit the subscript R, but usually you have to have that for these two things. So this is V in V and W in W. Okay, so far we're just like taking these as like a basis vector for a free module, okay? But it's subject to some relations. So, okay, so this is a little V and a little W. Subject to relations. Okay, so we just kind of mod out by these relations. Okay, so the relations are that you make it linear in the first and second component. So CV1 plus V2 tensor W. This is going to be C V1 tensor W plus V2 tensor W. So you just kind of like extend linearly. Oh, that should be here. Oh, I can't do that. Okay, there we go. Okay, and then we have V tensor some constant W1 plus W2. So it's just linear in the first and second vectors. So you're just kind of like formally multiplying vectors. Okay, so this is C V tensor W1 plus V tensor W2. Okay, so these are the relations that you impose, and here you have so I guess so where, okay, so now I just need to write everything. So in the first equation, V1 and V2 are in V, C is a constant, and W is in W. In the second equation, we have W1, W2. This is in W. We have C is in R, and V, little v is in V. Okay, so yeah, so this is all you do. All right, and that's what we have. So the zero element is any element equivalent to, so the zero element, maybe I should also say this. So it's a module, this thing's an R module, is any element to 0 tensor W or 0 or V tensor V tensor 0. Okay, so so what else do I want to say about this? So this is, so what do general elements look like? So how do you write down a general element? So a general element will look like something like this. So it'll look like a sum of Ci, I is equal to 1 up to n, and then we'll have like Vi tensor Wi. Okay, so this is what an element looks like. And then if there's no, if you can write it as a tensor product of two things, so pure tensor. So this is what a general element looks like. Maybe I shouldn't have done that. Okay, and then there's a pure tensor. So these are elements of the form V tensor W. Okay, so most of the time, elements look like linear combinations of this kind of formal product. But sometimes we'll have pure tensors and they look like V tensor W. Okay. So what are some basic properties? Well, let's see. Okay, so this is what these are. Then I had to show you, let me see if I have it here. Okay, so then we had like there was a bunch of things that were equivalent. But I need to give you a definition first. Okay, so let me give you a definition. So this is what these things look like. Okay. All right, so let me give you a definition. Okay, so let's let M, N, and L be R modules. So we say a map here Q from M cross N to L is R bilinear if and only if, so we'll have Q, and then we if it's linear in the first and the second components, so we'll have CM1 plus M2 N, so this is CQ M1 N plus Q M2N. So it's like an inner product, right? It's a generalization of an inner product. where, okay, so now we have M, if I did Cn1 plus N2, okay, so then we have CQ, and then we have MN1, MN1, QMN2. Okay, where M, M1, M2, these are elements of M, N, N1, and N2 are elements of N, and C is an R. Okay, so we have these rules here. So this is what a bilinear map is. So like this is a generalization of an inner product. Okay, and but I guess the recipient space is here, and so these come up a lot. And so the one thing that I wanted to say is that the following. Okay, so this adjunction. So previously we talked about the adjunction. We said that that this thing here. So if we did M tensor N L, so this was isomorphic to mod R, and then we could do M, and then we can do mod R N L. This is how I want to do it. Let's do. I just want my notation to agree with the way that I set it up in the notes here. It should be an N. Okay, so we said that these two things were isomorphic. Okay, so here for we have M, N, and L. These are R modules. Okay, so actually the following are equivalent. So actually the following are equivalent. Okay, and I'm just kind of sketch this. So so R module maps from M tensor R N to L. Okay, we'll call this G. We're going to have R module maps M into mod R M and L. Okay, and we're gonna give this some notation. Okay, so it's like to every element of N, we're gonna get a map. So this is N maps to say F of N. Okay, and then we're gonna have R bilinear maps. So we'll call this M cross N to L. Okay, so so let me show you how to get these one from the other. Okay, and so these two parts here, this is what I already said before. Okay, so that's the same thing here, that these two things are the same. But I now introduced this third thing, which are these R bilinear maps. Okay, and so here is the equivalence. Which you can check. Okay, so okay, so let's do, if we're given G, okay, so here, what do we have? G is this map from M tensor N to L. Okay, So how do I define f, right? So then so fn of m, so this is going to be defined to be equal to g of m tensor over Rn. Okay, so that's how you so what I did is, given this g, I can produce this. So I can produce this function f subscript n, right? And f subscript n, so you can check, that f subscript n1 plus cn1 plus n2 is equal to cf of n1 plus f of n2. So remember that module maps, they themselves are a module, right? And so this thing makes sense. Okay, so you can check after you break this down like this. Okay, so that's something that you should do. And then how do you define q? So q of mn, well, that's also defined to be g of m tensor over R with n. Okay, so now so given the g, I can recover this thing. So for this one, you check this, and this one you can check, say, that this is, check this is R bilinear. I mean, you should just do it right now by hand, and what you use is these rules for the tensor product like this. Okay. And okay, so given the FNs, okay, so now I'm going to show you now, given the FNs, right, how do I produce? So now we need to produce a G, right? So G of, well, M, let's just do a single linear combination here. So C M1 tensor N1 plus M2 tensor N2. Okay, so how do I define this map, right? So this should be CF of N1 M1 plus F of N2 M2. Okay, so this is how you define this, and then you should check that this is well defined, right? Okay. So so then how do you define? So okay, so how do you define Q of C of M1 plus M2, and let's say D of N1 plus N2. So how do I define this? So given the F's, so this should just be F of dN1 plus N2 of CM1 plus M2. Okay, and then you can check that this is, so you can check that this is bilinear. And that comes from the properties that these maps are, so from the property that these maps Fn, that that they have kind of this distributive property here, right? This one that I highlighted here, and then the fact that they themselves are linear. Okay. All right, and then given the Q's, or given Q, I should just say not Q's. So how do we produce G? Well, I need to take G of CM1 tensor N1 plus M2 tensor N2, right? And I need to define this some way. And so what we'll do is we just take, well, C of Q of M1 N1 plus Q of M2 N2. Okay, and then you should check that, check that this is a linear, check that G is a linear map. Okay, and then so it's a map of R modules, and then how do we define F of N of C. Okay, so now we just need a map here. How do we define this map? Okay, so this thing is just going to be defined to be Q of Mn. Okay, so like every one of these, so all of these data here, right? So a map from the tensor product, right, into another module, a map from N, so that gives you maps, right? So a map that gives you maps, and a bilinear form, or so this is these bilinear maps, right? All of those things are the same, okay? And they're just kind of different ways of writing the same thing. So now we can kind of just juggle these things up. Okay, does that make sense? Maybe a thumbs up or something, maybe.
Yeah, I follow.
Okay, cool.
So Taylor, just to make sure I'm understanding what you meant to say there, or what not what you meant to say. What you are saying is that we have these three equivalent maps, and now we can kind of interchange. We can move stuff around using them.
Yeah. So like sometimes when you're doing a proof, it's better to look at it as like a map to maps, or a map from the tensor product, or a bilinear form, depending on the context, right?
Okay.
And so sometimes they'll ask you to prove something, and you can just kind of like move it to some other way that you find more convenient, and then use that to for your application. Okay, so there's the functorial properties. So let me just talk about the functorial properties of tensor products. Okay, so so we have here. So we have several natural equivalences. Okay, so I'm just going to write them down. So so n tensor R to M. So this is isomorphic to M tensor R to N. Okay. And so okay, so let me just say like how these are functors, right? So okay, let me just write them all out, and then I'll say a little bit more about what I mean by functorial. Okay, so we have M tensor R N. So we have the kind of this like associativity axiom. M tensor R, and then we have N tensor R of L. And then we have M tensor sorry, I need to do direct sums and tensor products. So and you know what I did? I wrote it on my notes so that I can't tell the plus from a times. Okay, but I need to be more careful. So M tensor, so we have a distributive property, okay? And direct sum L. Okay, so this is M tensor over R with N. Direct sum M tensor over R with L. So this is a distributive property, and then we have kind of a cancellation rule. Okay, so note that this is kind of a cancellation rule. How do I spell it? Two L's or one L? Cancellation, there should be two, right? Okay, so this is a distributive rule. This is associativity. And this is a commutativity. Okay, so we have a way to kind of combine these things. Okay, and so what do I mean by functor? So what do I mean by natural equivalence? I guess let me do that part over here. Okay, so in this particular case here, I'm just going to explain it in this particular case. So this direct sum, or the tensor product, so we have kind of two functors. So we have this functor from pairs of modules to modules. Okay, so we have two functors, right, where you take m and n, and you could map it to m tensor n, and then we could have m and n, and this could map to n tensor m. So these are two functors, right? And so so we are saying that there's a natural transformation between those two, which is a natural equivalence, right? So there is a natural transformation between these two functors. And it is a natural equivalence. So it's just a natural transformation with isomorphisms anywhere. Is a natural equivalence. Okay, so what does that mean? So I have like two functors, f and g, right? And well, we really have like so we have m1 n1, m2 n2, m1 n1, m2 n2. Okay, so then we have the functor f. We have this thing here. So this is f of some morphism in this category. We have g here. We have g of a morphism in the category. And then this thing here is the natural equivalence. Okay, so what we're looking for is that so this would be like a pair of maps. So here we're given, so if we're given m1 n1 to m2 n2, okay, this is f, and f is really a pair of maps for a map between the first R modules and a map between the second R module, the map between the m's and the n's, right? Then we get this diagram. So this is what it means to be a natural equivalence, and these things are isomorphisms here. So I wrote down this is what a natural transformation is. Just to remind you guys. So what you have to do is you just kind of have to, okay, so what I'm saying is that all I'm saying about all this is that not only do you have this thing here, right, that these properties hold, right, but that they behave well with respect to morphisms, okay? And sometimes you need that in proofs, okay? So, and it's a pain in the butt to check these, right? But technically you should. Okay, I'm not going to do it in class. Any questions on that? Okay. So let me just make a remark too. There's sometimes we have A-B bimodules. And then so where you have kind of a left multiplication by A and a right multiplication by B. So M has a left multiplication by A. So A is a ring, and right multiplication by B. Okay, so then in that case, we have two functors. In this case, there's two functors. Right? We have this thing, AM, okay? And we have this thing, so M, okay? And associativity works here. Okay, so sometimes you have like different scalars acting on either side. And I just wanted to say that you to be aware that sometimes this comes up. I don't think we're going to use it. Okay. Okay, so let's start playing around with this a little bit. Okay, all right, so let's do an example. Okay, so let's do an example.